3.2 talks about the second derivative test. Second derivative test talks about the concavity of the curve y equal f of x. So imagine that you're driving up a hill and you look at the front of the car. So you notice the front of the car is leveling off all the way to a specific point. Now when you roll down, you'll notice that front of the car is pointing downwards. So assume you're just looking at the middle of the tip of the front of your car as it's coming down the hill. You'll notice that it's starting to point downwards and getting steeper and steeper. But you are going to get to a point in which instead of pointing downwards, it's going to start pointing upwards. Right? Otherwise, it wouldn't stop. So if you look at the tip, just the tip, it's pointing downwards more, and then at a given point, it's going to start pointing upwards. Otherwise, you wouldn't get to a flat view anymore. That's what makes the inflection point a bit tougher than the maximum or minimum. You're looking for that point. Now, if I look at the right, if I start moving upwards, so you notice the slope of the tangent, the front of the car is pointing up as you move to the right, and it's getting steeper up and up. And then you get to a point and you notice, you know what, now the tip of the car is pointing downwards again, all the way until it looks straight. So, you know, the tip of the car is going up as you move. But then if it's going to look straight at a given point, then it has to start leveling off again. And you're looking for that point where it starts leveling off. And in this case, it appears to be about right there. And the easiest way around this is for you to look at this as a parabola. If this is a parabola, shouldn't that look like this? And if this is a parabola right here, doesn't a parabola look something like this? And if this is a parabola opening downwards, and if this is a parabola opening upwards, so the point where you switched from one parabola to the next, that's called an inflection point. And that's what you're looking for. And it turns out that's where the second derivative equals 0. So we do the same deal as we did with the first derivative. We do a second derivative test. And wherever the second derivative is negative, we say the function is concaving down. And wherever the second derivative is positive, the function is concaving up. And if you switch from concaving down to concaving up, we call that point A an inflection point. That's what these two are saying. They're saying if the second derivative is positive on an interval, then f is concaving up on that. And if the second derivative is negative, the graph is concaving down. And if f is continuous at a point at which the curve changes concavity from concaving up to concaving down and vice versa, then that's an inflection point versus so if it concaves down, down, then up, this wouldn't be an inflection point, but this would be an inflection point because the graph switched from concaving up to concaving down or vice versa. Now, in the first set of problems, you're given graphs, and we want to know, find the intervals on which f is concaving up or down. And here you're going to approximate. If I draw a parabola, doesn't that mean that this function f is concaving up from negative infinity to positive infinity everywhere. If I look at this as a parabola, and if I look at this as a parabola, doesn't it look about right there? So you say f is concaving up from negative infinity, and what do you think that point is? Assume that's negative 1. You could say negative 1 about, it's really about negative 0.9. Again, we're just guessing, no big deal. If I'm giving you a graph, we're not going to disagree. The majority of the time you're going to be given a function, and you get me the exact answer. And it's concaving down from negative 0.9 to infinity. And if I look at this graph, if this was a parabola, shouldn't it look like this? And if this was a parabola, shouldn't that look like this? Where do they break? Here you break from the yellow to the blue. So we would say f is concaving up from 0 to infinity, and f is concaving down from negative infinity to 0. And if I look at this, if this is a parabola, it should look something like this. And if this is a parabola, it should look something like this. So the inflection point happened to be right there. I'm going to call that negative 1. And I'm going to say f is concaving up from negative infinity to negative 1. And f is concaving down from negative 1 to infinity. And there it is. Now, of course, given a graph, it will be a lot more accurate on your homework, so you could get the points. But again, you're just kind of eyeballing where it is. Algebraically, we could get there a lot quicker. I did not mean a lot quicker. I meant a lot more precise. It's going to take longer because you have to do some work. So what are we looking for? We're looking for second derivative test. The first derivative is 2x plus 3. Second derivative, if I do my chart, let me change the format really. So if I make the chart, and we're going to do this again, something you need to get used to. There's f prime, there's f. If I pick any test point, isn't the second derivative always positive? That means f is concaving up. So we say f is concaving up from negative infinity to positive infinity. And that's true with parabolas. B, same deal. Now I could graph it, but they're not asking. Oh, sketch a graph. Yeah. No, I could graph it. They want us to graph this. Okay. Okay, I did not read directions properly. I apologize. Let's get that out of the way really quick. It didn't say. It says find the extreme values, inflection points, intervals where f is concaving up and down, and sketch a graph. So actually, I should have set this equal to 0 and say, well, let's see, x equal negative 3/2. There's f prime, there's f, so negative 3/2. If I pick a point to the left of that, say negative 10, that will be negative. And if I pick a point to the right, say 0, that will be positive. So our conclusion out of all of this, and that's a lot of information, we said f is concaving down. We have f decreasing from negative infinity to negative 3/2, and f is increasing from negative 3/2 to infinity. Let me write this a bit. And we also know we have a local minimum at negative 3/2, and what is that? That will be 9 over 4 minus 9 over 2 plus 1. I'm substituting negative 3/2 in there. That will be 9/4 minus 18/4 is negative 9/4 plus 4/4, negative 5/4. So the numbers are not ideal, but it's not that big of a deal. Negative 1, negative 2, negative 3/2, and negative 1 and 1/4. That's how the graph looks like. It passes through the point 0, 1, and the graph is symmetric. We know that. So you go that many to the left, 1 and some, and you go up to 1. The graph has to pass through that point as well. And you notice f is decreasing, then increasing, but it's concaving upwards from negative infinity to positive infinity. So let's do the same on this problem. Again, if I take a derivative, that is negative 4x squared. And where does that equal 0? When x equals 0. So I do my testing for the first derivative test. I point to the left, notice, okay, that's 4x, not 4x squared. If you plug in a negative in there, that will be a positive. And if you plug in a positive in there, that will be a negative. So the conclusion out of this so far, and I should put those all together. So I should say f is increasing from negative infinity to 0. F is decreasing from 0 to infinity. We have a local max at 0, and if I plug that in, 2. Okay. Now, the second derivative test, I take another derivative, that is negative 4. In this case, it's a special case for parabolas, y double prime and y. No matter what I pick, the second derivative is always negative. The graph is concaving down. We say f is concaving down from negative infinity to positive infinity. So we have a maximum at 0, 2. Maximums look like this. So the graph looks something like this, increasing, then decreasing, and the concavity is preserved. It's ideal. So again, a parabola has either concavity up or down always. When I get to the cubes, it's slightly different, but that not much. So the same deal, I take a derivative, that would be 3x squared minus 8x plus 4. So if I want to figure out where that equals 0, 6 plus 2 is 8. Okay, so that's 3x minus 2 and x minus 2. Is that right? 3x squared minus 6, 9. Okay, there you go. And if it has a factor, you complete the square root quadratic formula. So I have x equal 2/3 and x equal 2. Okay, so if I do my testing, two-thirds and 2, there's f prime and there's f. If I pick a point to the left, say 0, I could put 0 here, I'll get a positive 4. A point between 2/3 and 2, 1. 1 is ideal. If I put 1 in there or 1 here, whatever you want. 1, 3 minus 2 is positive, and 1 minus 2 is negative, so that make it a negative. And a point to the right of 2, say 5. 15 minus 2 is positive. 5 minus 2, that's a positive. So here we have the conclusion. F is increasing, then decreasing, then increasing. F is increasing from negative infinity to 2/3, union with 2 to infinity. F is decreasing from 2/3 to 2. We have a local max, and that's crucial, at 2/3, and we have a local min at 2. So max at 2/3, I could use my scientific calculator and figure that out, or I could plug it in. 2/3, that is 8/27 minus 4 times 2/3 squared is 4 over 9 plus 4 times 2/3, which is 8/3. So that is 8 over 27 minus 16 over 9 plus 8 over 3. Again, you all are allowed a scientific calculator, so you could check that on your calculator. So that will be 8, 3 times minus 48, that's negative 40. Negative 40 plus 72, that would be 32. A decimal is fine. And if I plug in 2 in the original, notice I always plug this in the original, I'll get 8 minus 4 times 4 is 16 plus 4 times 2 is 8. I'll get negative 16. No, I'll get 0. Yeah. Okay, so all of that work could be done in a calculator. It's not going to require that much. Okay, and now what? The second derivative test, if I take f double prime, I'll notice that that is 6x minus 8 equals 0. Well, that means 6x equal 8 and x equal 8 over 6, which is 4 over 3. 4 over 3, f double prime f. Pick a point to the left, say 0, that's negative. And a point to the right, say 5, that's positive. So this is concaving down, concaving up. So we know that f is concaving down from negative infinity to 4/3. F is concaving up from 4/3 to infinity. We have an inflection point at 4/3, and again, use your calculator to plug this into the original. That's 64 over 27 minus 4 times 16 over 9 plus 16/3. So that is 64 over 27 minus 64 over 9 plus 16 over 3. That is 3 times 3 times, wow. That's negative. So you lose one of those. 128 divided by 9 plus times 3. And what's 48? And what's 48 minus 128? 128 minus 48 is 80. Negative 80 over 27. Okay, we erase all of that. Hopefully I didn't make an error in there, but if I did, you get the point. Again, you can plug all of this. You have a scientific calculator, plug all of that in and just get it really quickly. No need to do that much work. So what do we need? What stands out? We have a maximum at 2/3, 32, say 30 over 30. That's 1 and some, a bit bigger than 1, like right there. That's a maximum. Maximums look like this. And we have a minimum at 2/0. Minimums look like this, right? And we have an inflection point at 1 and 4/3. Okay, that must be positive. I messed up. And 0 point. So the graph looks, this is the inflection point. The inflection point, this is concaving down, right? And this is supposed to concave up. And if you are to look at, oops, it didn't register. So we're trying to mimic this on this graph. That's what you're trying to visualize. And that's what the graph should look like. And if I get to the next problem, if I take a derivative, that's 3x squared minus 6x minus 9. Where does that equal 0? Factor a 3 out. Do my testing. y. If I pick a point to the left, say negative 2. Negative 2 in there will make that a negative 5 and a negative 1. Negative times negative is a positive. If I pick 0, that will make that a negative. If I pick 5, 5 minus 3 is positive. 5 plus 1 is positive. So we have increasing, decreasing, increasing. So again, we draw all of our conclusion in one place. We say f is increasing from negative infinity to negative 1, union with 3 to infinity. F is decreasing from negative 1 to 3. We have a local max at negative 1, and if I plug that in, negative 1 minus 3 plus 9 plus 5, 14 minus 4 is a 10. And we have a local minimum at 3, 327 minus 3 times 9 is 27, minus 3, 9 times 3 is 27 plus 5, so the numbers are big because I made this up. Negative 27 plus 5 is negative 22. We take the second derivative. That is 6x minus 6 equal to 0. That's when x equal 1. If I pick a point to the left of 1, say 0, that will be negative. A point to the right of 1, say 3, put 3 in there. 18 minus, that's positive. We have f concaving up from negative infinity to 1. F is concaving down from 1 to infinity. We have an inflection point at 1, and if I plug 1 in, I get 1 minus 3 minus 9 plus 5. That is 6 minus 12, which is negative 6. So I have to rescale this graph on the y because the values are a bit big. So I need to get to these points. Well, I'm going to go by negative 5, negative 10, negative 15, negative 20, and negative 25. Again, the number should work out nicer on your homework. So I start off with negative 1, negative 10. There's a maximum. Maximums look like this. And at 3, negative 22, we have a minimums, and minimums look like this. We have an inflection point at 1, negative 6. Okay, something is not right. Let me just see what that is. At 1, negative 6, we have an inflection point. The maximum is at negative 110. There you go. The maximum is at negative 110, 510. There's the maximum, much better. So you start from the inflection point, and if you were to proceed and say, look, inflection point, concaving down should look like this, and concaving up should look like this. Again, you're trying to mimic the parabola opening down and the parabola opening up, and you'll notice everything matches. And that's how we do this. Now, last type of problems, you do get a rational every now and then. Oops. And same deal here. We notice that x cannot be 2. So if we take a derivative, derivative of the top times the denominator, minus derivative of the denominator times the top, all over the denominator squared. Y prime is x minus 2 minus x minus 3 over x minus 2 squared. Y prime is negative 6 over x minus 2 squared. Now, if I want to check where does y prime equal 0, nowhere, because a negative 6 can never equal 0. Where is y prime not exist? Remember, we haven't did this yet because polynomials exist everywhere. That's where the denominator equals 0. That's when x equals 2. So I have one point to test. A point to the left of that would be 0. If I plug in 0, again, that's negative. And if I put in 0, negative 2 squared is positive, so that's negative. The function is decreasing. If I plug in, say, 3, that's negative, and 3 minus 2 is positive, that's decreasing. So our conclusion is that f is decreasing from negative infinity to 2, union with 2 to infinity. And the reason I can say from negative infinity to positive infinity, because I know there's a restriction in the domain. Now I take my second derivative. I'm going to write y prime as negative 6 into x minus 2 to the negative 2. And if I take a second derivative, bring the power down, subtract 1 from the power, times the derivative of the inside, which is 1, y double prime is 12 divided by x minus 2 cubed. Where does y double prime equal 0? Nowhere. A 12 can never equal 0. Where is y double prime not exist? It doesn't exist when the denominator equals 0. That's when x equals 2. If I pick a point to the left of 2, say 0, plug it in. The top is positive. The denominator, negative 2 cubed, is negative. If I pick a point to the right, let's say 3, top is 12, that's always positive. Denominator, 3 minus 2 is positive. So we have f is concaving up from 2 to infinity. F is concaving down from negative infinity to 2. We do have an inflection point, but what's the issue with that? We have an inflection point at 2. If you plug 2 into the original equation, do you see that you'll get 5 over 0? Because it's not in the domain. So there's no inflection point. If I look at the graph of this, we know that x equal 2 is a vertical asymptote. We also know that there's a horizontal asymptote of y equal 1. The graph is no maximum or minimum. It's decreasing everywhere. Since it's decreasing everywhere, right? And we know it's going to cross when x equals 0, you get negative 1.5 and negative 3. So if it's decreasing everywhere, we know the graph is going to look like this because that's decreasing. Otherwise, it will be increasing. And the piece to the right, it's one of those two. But this is increasing, so it has to be the decreasing part. And do you notice the concavity? It's concaving down, and it's concaving up. And that's pretty much it for this section.